Good morning. I'm Amy Hollander with the National Renewable Energy Laboratory. Welcome to today's webinar on monitoring residential geothermal ground source heat pump systems, sponsored by the United States Department of Energy. I'd like to begin by thanking all of you on the phone for joining us this morning. We're broadcasting from DOE's National Renewable Energy Laboratory's brand new state-of-the-art net zero energy research support facility in Golden, Colorado. Our presentation today is designed to assist sustainable energy resources for consumers, or SERC grantees, and DOE project officers in monitoring SERC technologies. Although this webinar can be useful to anyone inspecting residential systems, it is intended to inform SERC grantee inspectors and DOE project officers how to identify proper quality, functionality, and long-term durability of ground source heat pumps, geothermal ground source heat pumps. We're going to give participants a few more minutes to call in and log on. So while we wait, I'm going to go over some logistics, and then we'll delve into today's topic. First of all, today's presentation will be posted online within 10 days to 2 weeks. You will be receiving a link to the presentation via email at the end of the webinar. But remember, the presentation will not be published or at the link for 10 days to 2 weeks. For now, you have two options for how you can hear today's webinar. In the upper right-hand corner of your screen, there is an audio pane. If it is not visible to you, look for the red arrow and click on it. Opening this red arrow will allow you to choose whether or not you want to listen to the webinar through your computer speakers or by dialing in through your telephone. As a rule, if you can listen to music on your computer, you should be able to hear the webinar. Sometimes the volume is not loud enough through your computer, so you can dial into the telephone number and passcode to hear the webinar. The phone number and passcode are in the audio box. If you have questions during the presentation, please go to the same box in the questions pane. There you can type in any questions you may have during the course of the webinar. We will then strive to address your questions at the end of the webinar during the question and answer segment of today's presentation. And with that, I'd like to introduce today's speaker. Today we will be hearing from Dave Peterson, who is a project leader at the National Renewable Energy Laboratory. David Peterson provides technical support to programs under the U.S. Department of Treasury and U.S. Department of Agriculture. Dave has provided presentations on geothermal heat pump technology to various audiences, including DOE's Tribal Energy Program, Iowa's Office of Energy Independence, and Massachusetts Department of Natural Resources. With that, I will turn it over to Dave Peterson.
Thank you, Amy. Thanks for everyone for joining us. Again, this presentation is on geothermal and ground source heat pumps. I will be using the acronym GHP to represent ground source heat pumps. I will probably refer to them as ground source heat pumps because that's the way I typically refer to them. But there are a number of different names you'll see this technology under: geothermal heat pumps, geo-exchange systems, ground source heat pump systems. They're all referring to the same technology. This slide basically shows the general structure of what we're going to cover in this presentation. What is a ground source heat pump system? Again, GHP is I'm referring to as a ground source heat pump system. How does a ground source heat pump system work? What are the different types of ground source heat pump systems? Where do ground source heat pump systems work? What are ground source heat pump system considerations that there are? And then how do you evaluate a ground source heat pump system installer? And then finally I will review the checklist that has been, I believe, provided to people who have seen the checklist. And I'll just briefly go over that and sort of emphasize important points in the checklist. So before we get started really diving in, I just want to clarify something. What is a ground source heat pump system and how does it differ from other geothermal technologies? And this is an important sort of distinction to make. You'll often hear geothermal energy or geothermal systems all lumped under one category, but there are three distinct types of geothermal technologies that are very, very different. What we're going to talk about today is the ground source heat pump system. Again, I'll be referring to it as GHP in the rest of the presentation. And these systems are used for space heating and cooling and domestic hot water. They can be installed in commercial buildings, and they can be installed in residential structures. The second type is a direct use system where you're literally pulling hot water out of the ground and using that hot water to heat a structure. And then the third is geothermal electricity generation or geothermal power, where you're actually using hot water pulled out of the ground. The water is so hot that it actually generates steam that can turn a steam turbine and generate electricity. And I have three pictures here. The one on the left is the ground source heat pump system and shows the loop field being buried underground that will be used for the heating and cooling of a structure. The middle picture is a direct geothermal system where this is a nursery, I believe, in New Mexico that uses hot water pulled out of a well nearby that is heated that is already hot enough that it can provide space heating for the structure. So it's directly using the water and the heat in the water pumped out of the ground to heat this nursery. And the right picture is a picture of the geysers in Northern California. I don't know if anyone's ever been. It's in Sonoma. It's just north of, I think, Calistoga. It is I believe it's still the largest geothermal power system in the world, and it provides a huge amount of power to the California grid. And it is basically using superheated water found in geological formations underneath the hills in Sonoma to generate electricity directly. And again, the two on the right are very site-specific. You have to have the right geological formations, the right water conditions to make those systems work. What I'll talk about soon is that ground source heat pumps are able to be installed in a wider range of areas and is a much more common technology. So what is a ground source heat pump system? This is just a general description of what we're referring to here. It's an electrical powered heating and cooling system that uses the relatively constant groundwater temperature to transfer heat or energy or heat for space heating and cooling or heating hot water. And so in heating mode, these systems provide both heating and cooling. So in heating mode, they transfer heat from the ground or groundwater into the building. In cooling mode, they transfer heat from the building and reject it or put it in the ground or groundwater. And so how does the ground source heat pump system work? This is a basic diagram or diagram of the components of a ground source heat pump system. So you have three basic components of a ground source heat pump system. You have the external loop field. In this picture, it's shown as this sort of in the bottom right-hand corner where you've got the blue and red piping running underneath the ground. It's basically this piping or tubing buried underground that has heat transfer fluid flowing through it. That's the external loop field. And then you have the second main component is the heat pump unit itself, which includes an evaporator, condenser, compressor, expansion valve, refrigerant, all in sort of a one contained unit within that would be located inside the house, inside the structure, probably in the basement, much like any other furnace. And then you have the interior sort of HVAC distribution system. How are you getting the heating and cooling to distributed through the house? And these systems can either be ductwork or radiant floor. Often, if it's a radiant system, your ground source heat pump system would only provide heating. It wouldn't provide cooling. If it's a ductwork system where you're basically replacing the forced air furnace and the AC unit, it would provide both heating and cooling. And essentially, it's not that the ground source heat pump system is not terribly different from an air source heat pump unit, which are much more common, except in the fact that you're using the ground as your place where you're deriving your heat or dumping your heat. In an air source heat pump system, you're using the outside air, and this pretty much provides, this is the reason why ground source heat pumps are more efficient than air source heat pumps, because you're using the constant temperature of the earth rather than the sort of more variable air temperatures. And so this is a basic diagram of how a ground source heat pump works. This is essentially showing the guts of a ground source heat pump unit or a heat pump unit. And these are the major components. Again, the loop fields on the bottom, which runs through the ground. It runs the heat transfer fluid through the ground up into a heat exchanger. And if you're in heating mode, that heat exchanger would extract the heat out of that heat transfer fluid, and through sort of a refrigerant cycle, allow internal air of the house to be brought in, heated, and then returned and distributed throughout the house through the air supply. Again, components of this are very similar, aside from the ground loop, very similar to other HVAC equipment. And then you've got the thermostat that would allow the homeowner to control the temperature settings. So ground source heat pump systems are there are many different types. I'll focus mainly on closed loop systems. So what I've got here is a diagram of all the different types of ground source heat pump systems, and it's usually dependent on what type of ground loops provided. And so you've got a closed loop system, which I've been somewhat alluding to in the previous slide, where you've got essentially a sealed tube buried underground or sunk underwater that circulates the heat transfer fluid. And that's somewhat of a contained system. And again, you're using sort of an antifreeze, a propylene glycol solution, as a heat transfer fluid in general that, again, either pulls heat from the ground or rejects heat into the ground, depending on whether you're trying to heat or cool the structure. The other type of system is called an open loop system, where you utilize groundwater directly as the heat transfer fluid. Open loop systems are generally more efficient, are cheaper to install than a closed loop system. They're generally probably more efficient. The problem is that they require very specific conditions for their installation, and so therefore they're not as common as a closed loop system. So for the rest of the presentation, I'm going to be referring to a closed loop system, and I'll basically be detailing some specifics on closed loop systems. So the first type of closed loop system that I just really want to go over quickly is, again, we're talking about burying the tubing or the loop field underground and circulating heat transfer fluid through it. So we've got a horizontally oriented closed loop design, which for most residential systems, this is likely going to be the design that you're going to see. And this is basically an orientation where you put the loop field, you bury it about 6 to 8 feet deep in sort of shallow trenches. I've got two pictures here on the bottom where you've got they've actually put they've dug a trench with sort of a backhoe, and they're burying it down into that trench, and that's actually the one on the right. The one on the left is where it literally looks like they're digging out a swimming pool. So they're digging out a large section of earth, putting the piping on the bottom, and then they'll bury it. Again, ideally you want to be 6 to 8 feet deep. You want to be below the frost line. You don't want, and again, the deeper you are, the more constant the earth temperature is, and so that helps with the efficiency of the system. The issues with the horizontal loop field design is that it does require more land than the next type that I will be talking about, and it's more applicable to smaller buildings because, again, you're going to need more space. If you had a huge structure, you would need a lot of land, and if you have land available, yeah, you probably can do it. But then you're also talking about the cost of excavating out a large amount of space. There again, these are generally less expensive than the next type we're talking about, and they generally require less skill, specialized skill and equipment to install. So contractors will be more widely available to do this type of orientation. The next type of closed-loop ground source heat pump systems is a vertically oriented closed-loop design, and this is a type of design where you're actually drilling essentially boreholes or wells deeper into the earth, and so we're talking 150, 400 feet deep boreholes that the piping is then inserted into. The benefits of this is you're going deeper, so again the Earth's temperature is more constant the deeper you go, and so you've got less variability as you would with a horizontal system. Generally, we're talking about higher installation costs in these, even though there are vertically oriented loop fields on residential structures. In general, these are for larger structures. Again, if you would have a multi-unit housing development unit, that would be something that could use a vertical system, a vertical loop field. You'd also be looking at this for schools and government buildings and things like that. So larger structures, higher costs because of the drilling. You need specialized rigs to do this, and there's one on the left. The bottom left is a picture of a rig, and essentially you're drilling these boreholes, and you're going to, because of the specialized rigs and the drilling operations, you have probably a more limited availability of experienced folks to do this type of system. And you're looking at drillers and installers that really know what they're doing when you're putting one of these systems in. And so the next question is, generally across the U.S., where do these systems work? We are looking at a graph here. Essentially, I guess let's look at the bullet points first. These systems technically can work anywhere in any climate, but the soil conditions are very important to how these systems function and their performance, and must be considered. And so the graph on the top really just shows sort of annual operating costs. A lot of this has to do with how much it's going to cost to operate the system. And so in Burlington, Vermont, it looks like you've got the first bar, the blue bar is essentially a ground source heat pump system. The second bar is an air source heat pump system, and the dark red bar is a furnace with an AC unit. And these are sort of annual operating costs per year for these different types of HVAC systems. And you can see in Burlington, the ground source heat pump system appears to come out much cheaper on an annual basis, an operating cost basis, than the other two. But you can see in other places it doesn't appear to have much of an advantage cost-wise. And this is a significant issue because the cost of installing a ground source heat pump system is just going to significantly more than any of the other conventional HVAC systems. And so it really depends on the location of the system. I'll come back to this in a couple more slides to talk about the cost issue. And this is just another slide. This is pulled from the EIA website, where it shows the distribution of where ground source heat pumps are installed in the U.S. And again, this is a mix of residential and industrial and commercial systems, so it doesn't really tell you, where all the residential systems. But Midwest and the South are primarily where these systems are installed, and likely one of the main reasons is that, again, these are all electric systems, so where power is cheaper, they make more sense. And in general, you have to have the right soil conditions. So apparently the South and Midwest, it's easier to install these things and to make them function properly. And also, a lot of this could also be utility incentives and things that are driving those markets as well. And so this just gives you a basic snapshot of where these things generally are installed in the U.S. And here are some general considerations when you're considering, when you're looking at a ground source heat pump system from a project officer standpoint, or from any person's standpoint. Know the process, kind of what we've already gone over. Know the general process of how these things work. Know what to look for in regards to a residential system. I'd like to point out one of the better sort of guides that are out there for a non-engineer. It's called, I think it's called the Geothermal Survivor Kit. You can download it from, there's a company called Heat Spring Energy that does a lot of training on ground source heat pumps, and they have this engineer update this. And so this is a really good link, and you can download this. It's like a 30-page, 40-page document that gives you sort of the lowdown on ground source heat pump systems at the residential level. You know, look at the site prior to installation. Require a minimum system warranty. Again, when we talk about a system, problem with ground source heat pumps is that, you know, the heat pump unit is usually manufactured by a well-known entity and may have a defined warranty, but you really want to make sure that the system, the loop field, the heat pump, the distribution system, that it all works together and functions properly. So you want to look for a system warranty. Look for minimum, reference the minimum installation standards. Again, use, so this acronym, IGSHPA, it refers to the International Ground Source Heat Pump Association. They are essentially the main body that polices installers. They certify installers and designers. They run the training courses. They are also somewhat of a lobbying arm for the ground source heat pump industry. So they have a vested interest in pushing the technology, but they also have a vested interest in making sure that these systems perform as expected. I'm sorry, I just advanced the slide when I wasn't supposed to. And then we've got a couple other things. So request unit pricing, request design drawings. Yeah, essentially understand what's being done and make sure that the installer understands exactly how the system is supposed to be designed and how it's supposed to function. So again, I'm coming back to cost again because this is a major consideration, and I can't emphasize this enough. And so again, installation costs for ground source heat pump systems are going to be significantly higher than conventional systems. So the bottom graph shows the installed cost for a 3-ton system, which is roughly the size of a system for sort of a 1,500 to 2,000 square foot house. You can see the two bars on the left are the conventional HVAC systems, and that's their install cost around $6,000. But the ground source heat pump system, so you have the first one is a groundwater, using groundwater, and you're up to $10,000, and then the three on the right are basically the closed loop ground source heat pump systems that we've been referring to, and those are, you know, you're looking at $12,000. So you're looking at a cost premium of, you know, $6,000, $8,000, possibly even $10,000 difference for a ground source heat pump system, and the top graph basically illustrates why that's the case. It's essentially the loop field. So the main difference between a ground source heat pump system and an air source heat pump system is that the loop field requires significant costs to put in, and so the ground loop is the major you know, incremental cost difference between ground source heat pump systems and a traditional HVAC system. And so what are the major considerations in designing and installing a ground source heat pump system is sizing the system properly to the building that that needs the heating and cooling. This cannot be emphasized enough. This is absolutely critical that the installer knows what they're doing when they're designing the system. I'm going to keep coming back to that over and over again. Your installer and sort of the experience of your installer installing ground source heat pump systems is probably the critical, the make or break component or consideration for installing a ground source heat pump system. And so the main thing is to determine heating and cooling loads for the structure, accurately calculating heating and cooling loads for the structure that you're looking to at. Then you want to properly size and design the ground loop according to what the annual heating and cooling load that you calculated. And there's software to help designers and installers properly size it. I highly discourage not using rules of thumb on sizing the loop field. You may want to ask the installers, how did they size this system? What are they using to derive the size and the layout of the ground loop? And they should have a very good answer that's not sort of a quick math. Well, the house is 2,000 square feet, and therefore it needs to be much more specific than that. And I would say they would likely want to be using some sort of software to size the loop field. And then also you want to make sure that the ground loop has you're circulating the heat transfer fluid through the ground loop. You want to make sure that the circulation pumps hooked up to the ground loop are properly sized. If they're oversized, they use far more electricity than should be required. If they're undersized, they will not meet the heating and cooling loads of the structure. And then you also want to properly select the heat pump size for the structure and loop field that you're putting in. So I pulled this list actually off of the International Ground Source Heat Pump Association's website, and this is how do you evaluate installers of these systems. And one of the main things is that they need to follow the protocols established by the International Ground Source Heat Pump Association. And again, these are only available for closed-loop systems. I believe they're still only available for closed-loop systems. But they have lots of literature and very specific guidelines for how to install a residential ground source heat pump system. And ideally, these installers should be accredited by the International Ground Source Heat Pump Association or another sort of recognized institution. And a lot of manufacturers of ground source heat pumps, the heat pump units, actually do trainings for contractors. Ask for references, check their references. If they say they've installed systems, get some references and find out whether or not those systems are working properly before you sign them up to install a system at a structure that you're responsible for. Get estimates in writing and warranties, again, that don't just guarantee, the heat pump performance, but the whole installed system, and then insist on sort of a written contract that includes all terms, costs, start dates, things like that. And what I've included here in the bottom are 2 directories that will link you to installers in most areas of the country. And so the International Ground Source Heat Pump Association's directory is very extensive. They've been doing this for a while. So you should be able to find an installer in an area near you and that has done training or received a certification from this group. And so what are key ground source heat pump system considerations involving sort of annual maintenance? And I think what I wanted to emphasize with this particular slide is that, as with any HVAC system, you would likely want to do some sort of annual checkup. But with ground source heat pump systems, in general, once a system's been installed, you're probably looking at similar O&M or operating maintenance that any other sort of HVAC system would require. And so again, we're looking at making sure the filters clean, making sure the fan, and making sure that the air, we're talking about a forced air system here, making sure that the ductwork has been inspected. All these things are sort of for any sort of forced air ductwork type system you're talking about. This is sort of standard maintenance. And so I would say the maintenance should not vary much compared to an air source heat pump or another sort of HVAC system. And so now I'm going to go just briefly over the checklist that was sent out. And again, we're talking about just the checklist is requiring project information, inspection, and then an inspection checklist with pre-installation, installation, and post-installation. And so the project information, again, we're looking at, we want a general description of the system, size of the system, again, in tons, and a 1 ton. The installer should be able to tell you what that is in tons, and if you want to translate that into BTUs, that's fairly easy to do. The type of ground loop that you're putting in, I think that's a critical element, and then again, name of installer, inspector, and then the performance test and date of the performance test is another sort of critical component of this checklist. So the pre-installation checklist that was provided, you're looking at, the design, installation, was it completed by a certified contractor, International Ground Source Heat Pump certified contractor? Are the system designs complete? Did they give you drawings? Are they detailed enough to where you know what the contractor is going to be doing? Is the system compliant with the codes? Did they pull the proper permits? And then are there sufficient warranties, again, not just for the unit, but also for installation and sort of operation of the entire system. And the warranties for the heat pump units themselves, I think you're probably looking at maybe 10 years as a 10-year sort of limited warranty. In terms of sort of the ground loop and sort of the installation of the ground loop, the loop field warranty should be 25 years, 50 years long. I mean, that's just for what they put in the ground, what they buried in the ground. And when you're talking about sort of the system warranty, a lot of the installers will probably give a 1 to 2 year warranty that the system will function properly for those 2 years. And again, I think those warranties are going to vary, but I think any responsible contractor or installer will warranty a system for at least a year or 2. And so we've got the installation checklist, which talks very generally about the main different components of the ground source heat pump system. You've got electrical, you've got the heat pump, the ground loop. There's a number of so the ground loop we're talking about, is it installed properly? Again, according to the different type of orientation, they've got slinky, horizontal, pond, vertical. All these have different issues involving each one, and there are certain things that need to be paid attention to in installing each of those ground loops. For the heat pump, you're looking at, is it installed according to the work order, and then sort of are there any changes to the duct work or the air distribution, the heat distribution system inside the house? Is that done according to the work order? And then electrical, again, you're just looking at sort of standard issues that you would have with any sort of HVAC system. And so let's move on. Post-installation, I have some of these things checked off. I found this a little bit interesting. The visual inspection prior to the burial of the loop, the ground loop. Again, I don't know who's going to be doing that inspection, but it's maybe tough to coordinate that with the installer. And then a visual inspection after the burial of the loop field. The two pictures on the right are the top picture on the right is a picture of an open field. And I used to say, in one of the presentations I gave, I said, this is what you'll see outside the structure with a ground source heat pump system. Basically, the loop field's there, it's just buried underground, you can't even tell it's there. And so, once the loop field's been buried and if it's been resoldered or whatever, you probably won't have any idea it's there. And so sort of any visual inspection post-installation tough to do. And so, again, sort of the specifics of this post-installation, it may be difficult to do any sort of visual confirmation on any of this stuff. But you want to make sure that I think the contractor has can verify that all these things were checked off. And pressure tested the ground loop is a huge issue for these ground source heat pump systems, because that will tell you if when they bury the thing in the ground, if there are any leaks, are there any cracks in the tube? Did they, so the fused, the butts in the fused portions of the tubing, is that done properly? The pressure test would tell you right away if that was the case, and they need to make sure they do a pressure test in the ground loop. And then sort of performance testing, again, system documentation, ownership education. I think so system documentation, these are all the things that the checklist is requiring of folks. Again, make sure the owner understands what they have. Again, I don't think, the basic operation of this system is not going to be any different than someone having any other HVAC system, except, you may, if there's a problem that arises, you're going to have to call someone that understands how these systems work, and it's likely not going to be just every HVAC company that can do that. And so I think, so we got, again, so these are key points to remember. Verification of installation is very important. Monitoring assists with the success of these installations. If you don't know what to look for, just ask the installer or ask me. If, again, a picture, document. If you don't know what you're looking at, take a picture, document as much as possible, and then make sure that the client understands, or I'm assuming this is the homeowner, understands what maintenance is going to be required for this type of system. And so this is my contact information. If you want to contact me, feel free to do that. If I can't answer the question, I will refer you to someone that can. And I'm now going to turn it back over to Amy, and she will have a little bit of a Q&A.
Thank you, Dave. That was really informative and interesting. That includes the slides for this presentation on monitoring residential geothermal in-ground heat pump systems. For those of you who can stay with us, we have some excellent questions coming in from today's audience. The first one is, and I know this is tough to answer, but let's just say that you're looking at a system in the Midwest. How many years do you think it's going to take to pay off that system?
And that is a tough one. I think Midwest, I know maybe one of the links I'll provide is a study that the state of Indiana, they had a ground source heat pump incentive program, and they published sort of a little report talking about the costs associated, and that was a very Midwest specific. It's really about the incremental cost and your incremental cost of your system versus a traditional system, and then sort of how much does it cost to run that using electricity versus what you would have had to for your heating and cooling system otherwise. And so the installers won't give you an accurate answer on this, but again, I think the tax credits for bringing down the price significantly. There's federal tax credits, and then there's often state incentives, often utility incentives that bring the cost of these systems down. I would say you're looking at least a 10-year payback.
And that is without incentives, or?
I would say that's with incentives.
With incentives.
Yeah.
So since incentives vary from state to state, would it be safe to say the payback is going to be 15 years without?
Yeah, I would, you're looking over 10 years, and I would say, if you're under a 10-year, if you have an installer telling you that it's under a 10-year payback, show your math. Have them show the math, because, and make sure that the assumptions that they're using are accurate. Back when natural gas prices were very high, these systems looked great in a lot of areas because they're competing heating heating costs were going to be natural gas forced air furnace. And this looked a lot better because, again, this is using electricity to power the system. And in the Midwest, electricity prices are cheaper than they are fairly cheap compared to some other parts of the country. So I'd say the Midwest, the reason these things are installed as regular as they are is that they're fairly easy to install. You're not talking about really rocky terrain in general. The thermal properties of the soil are advantageous to a ground source heat pump system. And then you're looking at lower electricity prices. And so those are really what drive ground source heat pumps systems. But again, from an efficiency standpoint, these systems are hands down the most efficient, and when they're installed properly. The issue really is how much are the upfront costs, and what's that incremental cost going to be over a conventional system.
So it seems like one of the biggest benefits is environmental. The emissions are zero, and it also seems like that usually the incentives are high, and so it's probably going to bring the payback down to an 8 to 10 year period.
Yeah, I would say best case is going to be 8 to 10, and it goes up from there. But again, from the residential side, a lot, certainly the installers I've talked to have been installing these on big sort of big homes. So these are sort of luxury, well-off people homes, and so these are bigger structures. Again, the cost advantage for a ground source heat pump system comes in sort of the commercial size systems, and that's when they start really competing with conventional systems.
Okay, thank you. Next question. When used for home heating or in residential, as we're discussing, is a backup heating system required?
Yes. Every system should have some sort of auxiliary heat that's integrated into the system. And most of the time, I would say, most times the systems I've seen, they're using electric resistance heater, a small electric resistance heater that would actually kick on when the system became overwhelmed at really, really cold snaps. But in general, if the system's sized properly, meaning is the loop field adequate, if the system is sized properly, that auxiliary system should not have to kick on. But most systems do include a backup heat source.
Great, thank you. Under what conditions should you never install a ground source heat pump?
I think one of the main things is, is there a question that wherever you're putting the loop field, is that going to ever be used for some other purpose? So, if you have a field next to you, a plot of land that you want to sell at some point, don't put your loop field there because someone may want to excavate. And so essentially is where you're putting your loop field. I think, again, I showed the sort of geographical distribution of these systems. Again, they're probably have been installed in every state. They just tend to work better when generally where the soil conditions are best suited for a ground source heat pump system. But I would say, yeah, never install a ground source heat pump system when you don't know sort of the future of the space or the land where you're putting your loop field.
And what kind of activity can occur on top of the land? Can you drive on it? Can you garden on top of it?
Yes, yes. And again, schools do this, and they basically put a ground source, the loop field, and then they put a parking lot on top. A lot of colleges are putting these things in. I think Ball State's got one of the largest ones now, and they put their loop fields under the college green. So they basically, they didn't really have a lot of space. They had parking lots. They put some loop fields under parking lots, and then they put big loop fields actually under the college green. So so we're in between, the big college green area in the middle of campus. So yes, you can, that's fine.
Great. So how can you tell if the system is working? Say if you're in Tennessee or someplace where it's not very, very cold. Do you have to rely on a utility bill, or is there a monitor attached to the system indoors?
I would say most systems the monitoring is similar to that of your standard furnace. I mean, you really, if it's not functioning properly, it's either it's uncomfortable in the structure, and that's how you would know, or your energy bills are extremely high. And so that's really a lot of the systems that NREL's looked at have been heavily monitored for sort of research purposes, but most residential systems are not going to be monitored. There's not going to be any way that you can, and most homeowners would not know what they were looking at anyway. And so I would say, it's very contingent on, is it comfortable in the structure? You'll know. And then what are your bills looking like? And I think those are the two main ways that you'll be able to judge.
Okay, thank you. And it also sounds like if something goes wrong with the system, it's going to happen in the first few weeks. It's not likely that the system will quit working 5 years later because it's buried underground. It's probably, if something's not right, it's going to show up right away.
Yeah, I would say that's the case. And again, I think sort of the warranty for the whole system being 1 to 2 years should be adequate to work out the kinks if there are any to work out. And so, yeah, I would say that on average, repair costs in these things, once you get past that period, typically, one of the proponents of these systems say that the maintenance costs are lower. The main reason maintenance costs are going to be lower than a traditional sort of HVAC system is that you don't have any outside units. So that loop field's buried underground, and then everything else within the system is inside the house. So that the heat pump unit is in your basement. It's not like an air source heat pump where you actually have, or a condenser for an AC where you've got it outside and it's exposed to the hot and cold weather climate cycles. It's in the house. It's at roughly at room temperature, and so in general, maintenance is supposed to be less for these systems compared to a traditional HVAC system.
So in terms of recommending maintenance to low-income weatherization clients, what would you tell them after their system's installed, assuming that it's working well?
Well, I mean, I think again what we just talked about, look at the sort of comfort level within the structure. Again, if it's operating properly and it's up to your satisfaction, then I think general annual maintenance and maintenance schedules that you would have for any HVAC system would be adequate for this. And so again, a lot of what you're dealing with, what's inside the house, is not this it's very similar to what you would see with a conventional HVAC system. It's not that different. And so the annual maintenance, or the maintenance schedule that you would want a low-income person to follow, wouldn't be any different. I don't think it would be any different. I think what the difference is, if there is an issue, then you need to get someone. You need to call a contractor that understands these systems, and not every HVAC company does that. And so, I think that's the point.
Okay, it sounds like you're not recommending annual inspection or an annual checkup. Pretty much, these are maintenance-free unless they appear to be not dysfunctioning.
Well, again, I have a forced air furnace in my house, and I have someone come at least once a year, maybe once every other year, to double check that everything's functioning properly, and just general service, having it generally serviced on a regular basis, I think is wise.
I think that one thing, if it's not too late, to put in your RFP is to require that the warranty perhaps includes an annual checkup for the life of the warranty, and that's, I think, what we recommended in an RFP template that we did for ground source heat pumps. But just as a reminder, you might want to have the selected contractor follow through with a not a maintenance agreement, but just a warranty that requires that they verify that the system is working. So the next question coming in is, let's see, are there IGS HPA certified contractors throughout the United States?
I would say very likely that they are found in every state Again, if there is someone selling this service that they can install, design and install a ground source heat pump system, they are very likely, they should have that certification. I think I don't know if they're doing it online nowadays, but they offer these classes on a fairly regular basis. I think to err on the side of having a certified contractor is certainly in the interest of this weatherization program. Just because these guys have been at it for a long time, they've got a structure, they've been training folks up for quite a while, and if you go on their website and go to the directory, I have the link on that one slide. Maybe we'll provide that link to everyone. That should give you an idea of the sort of range of installers that are around. But again, that is not sort of an end-all, be-all. I really think that the references and sort of their experience is sort of the fundamental issue when you're evaluating a potential ground source heat pump system installer. Because just because someone got the certification doesn't necessarily mean that they are up to snuff to install a system and make sure that it's working properly. So I think the combination of those two is sort of the two critical components of evaluating an installer.
Great, thank you. And then this particular question came in before you hit on this slide, but I'm going to read it again because it is important. Would you elaborate on the importance of the correct sizing of the loop field and how that can negatively impact the system performance, say if it's not sized correctly?
Well, again, the loop field, the whole purpose of the loop field is to pull heat from the ground or to dump heat into the ground. And so, the larger the building, the more loop you're going to need because you're going to need access to more heat. Let's just talk about heating. You need heat to pull into the structure and to pull into the house. If the loop field is not long enough, it will not be able to gather up enough heat to keep the structure heated to a point that's comfortable. If the loop field is too long, so it's really sort of, it would underperform if it's not long enough, if the loop field's not long enough, and if the loop field's too long, you're talking about a system that will be far more expensive than it needs to be. And so again, the main driver of cost is the incremental cost of one of these systems is the cost of installing a loop field. And if you've oversized the system, you are talking about extra costs that don't necessarily need to be spent. Again, an installer that doesn't use the software, doesn't know the proper protocols to size the loop field, may just use a rule of thumb, and they may oversize it and it may perform well, but the cost of the system probably was driven up by that. So again, an experienced designer and installer of these systems should be able to properly size it, and again, that is a critical component of installing these systems, is making sure that whoever's installing it knows what they're doing, and to make sure that these things function over the long term.
Great, thank you. Going back to this question about the backup heating system, you were recommending an electric resistance heater for cold snaps or if something drastic would happen and it wouldn't quit working. So are you recommending removing the old heating system? So if the house has a forced air system, would you recommend removing that?
Yeah, this is basically removing your old system, swapping it in for a ground source heat pump system. I don't know of hybridized systems. I don't think that that's something that happens. I think in general you're talking about this is replacing your furnace. This is replacing your central AC unit. That's essentially the function of these systems. And I'm not totally familiar with possibly keeping different aspects of the existing system. Obviously, the main issue when you're retrofitting a building, a house, is what's the distribution system look like? Are you talking about, are you going to have to install ductwork? That's a major cost driver on retrofits. Is do you have to completely, if there's radiant, if it's a radiator sort of a boiler system, are you going to have to install ductwork for your ground source heat pump system? And that is usually the case with a lot of these. So, ductwork expense is putting in new ductwork is another big cost factor when you're talking about a retrofit.
So these systems work well using the existing ductwork of a forced air heating system, and so that would be a good recommendation for.
Yeah, I mean, if there's
Okay.
Yes.
Great, thank you. I'm not seeing any more questions, but I want to thank everybody for these really engaging and really good questions. Dave, do you have any closing comments for the audience today? Okay. For those of you who mentioned at the beginning, I'll mention again that you will be receiving a link to the webinar via your email, but it will not be posted for 10 days to 2 weeks. Also, you will be receiving a thank you for attending the webinar, and with that, I've asked Deb Listoka to include the checklist that Dave referred to. I will also ask her to include the links that were discussed in the presentation. With that, we will sign off, and I hope that all of you have a very good work day today, and thank you for joining us.